Welcome to lecture 39 on risk management and insurance. What we are doing in this lecture and have done in the last lecture is a bit more demanding than the material covered in the earlier lectures in this course. So it will depend on you, and you have to invest a bit of time here. I'm following the book by Neil Frey Embrechts. That's where I have my material from, and I try to do it a bit simpler than in that book. But it's still quite demanding. And if you don't have a second-year background in statistics, then this and the last lecture probably will cause you quite a lot of work. Now, an even easier treatment you will find in this article that I recently wrote. It's still a working paper, Copulas and the Quantity Theory of Money. You can read this one. The problem here naturally is that I'm dealing here with an economic problem, the quantity theory of money. The quantity theory of money is the idea when the central bank and the banks create more money, then in the end we will have inflation. And that's naturally highly relevant today. Today, during the coronavirus crisis, central banks support the economy by creating a lot of new money, injecting new money into the system. Now, in the short run, this really helps the economy and it will not create inflation. But in the longer term, it may create inflation if the money creation goes on and on. It's about the long-run relationship between the quantity theory, between money and the inflation rate. By money, here we just mean cash. Okay, so it's all banknotes, all paper money, all coins, but also your bank accounts that you can use to make payments, for example, by writing checks or using your credit card. So here I'm looking at the long-term relationship between money, which comes from the central bank and the private banks, and the inflation rate in the economy. And in the long term, when central banks create a lot of money, you will have inflation, but not in the shorter term. In the shorter term, then it really may help the economy. And if you have a financial panic, really the central banks should actually inject new money into the system, should keep the financial markets liquid. So you may actually read it here. The paper first shortly explains the quantity theory of money, and then I'm reviewing here in this paper what is a copula. And I do it on an much easier than here what you find in the McNeil Frey book. And I also do it easier than what I'm doing here in this current lecture. So this article really may help you if you would like to work with copulas. Now, copulas are a very topical in current research. So it could be worthwhile for you to look here, if you want to do research. It's just a means to model joint distribution functions. If you have you do not just look at a random variable, a single random variable. So you look at a group of random variables and you look at what is the joint distributions, and you can model this with copulas. So let's. Last lecture we looked at this. That's not here now just a single random variable. I'm using here a normal distribution, but I also could actually use here a gamma distribution or whatever. And then I would get a little bit different cumulative distribution function. But always here, those values between 0 and 1, those values for the probabilities, they will be uniformly distributed. That's this so-called probability integral transform. You start with a random variable x. It may have the normal distribution. It may have a gamma distribution, whatever. In the end, you transform those x's into new numbers here. We call them then actually set in the last lecture. And so set values, they are uniformly distributed. And we call it probability integral transform because you go by integration from the PDF here to the CDF. Okay, this involves integration. Now, you can apply this to a single random variable. And you can also apply this to the marginal distributions. Uses the marginal distributions. Okay, that also just involves a single random variable, so univariate. So I have here the marginal distribution of x, and here I have the marginal distribution of y. And here you see the joint distribution of x and y. Okay, so I have here a bivariate random variable. But here the marginal distributions, they are univariate. The random variable through this bivariate, x and y, we have two variables, two random variables, but then the marginals, they are univariate. So again, to the marginals, you can now apply this probability integral transform. Okay. Now I cannot, unfortunately, there's no program around to give the cumulative distribution up here. But to this histogram here, I can now do here the cumulative distribution. And I also can do it here on the other axis. It will look like this. Okay, but something like that. Okay, so you have the axis here. You move along the x-axis. You have the axis here. You have the marginal PDF here. That's given by those gray columns. It's a histogram. And then here you have the marginal CDF, the marginal cumulative distribution function. So that's those values here. They will be uniformly distributed. So you can, well, here I have the CDF, the marginal CDF. Here I have the marginal PDF for the x variable. That's the marginal PDF. And similarly, we do it down here here we do it for the y variable. And so the marginal distribution, they are univariate. Just a single random variable involved. Here on top, just the x variable. So we can do the marginal PDF, but we can also do the marginal CDF. And the values of the marginal CDF here, they will be uniformly distributed. So if I apply this to the marginal distributions, then the value of the marginal CDF is uniformly distributed. Okay, now here I have yeah, let's clean up a bit. So here I have the joint distribution. And for this joint distribution between x and y, you can write this here. So here I have the joint distribution between x1 and x2. I don't call it here x and y, but let's say between x1 and x2. I also have here, I only consider two random variables. Up here I'm going up to d. So here you have the joint distribution, and that joint distribution you can actually represent as a joint distribution of the values of the marginal distributions of those u's. That's the second step. Here I have a joint distribution, and this joint distribution I can represent. I can take those u values here, those uniformly distributed values here, and also here, and I can combine those in a joint distribution, and that joint distribution you call a copula. So I can express this joint distribution here. I can express it as a copula of okay, those values here on this axis, on those axes which are uniformly distributed. So that's the entire idea here. So I have the joint distribution between x and y, x1 or x2, and this can be expressed as a joint distribution of the u1 and the u2. So that would be the u1, and those are the u2. You see what I have here are the marginal CDF. Those are the marginal CDFs. And the function values are the u1 and the u2. So that's the other marginal CDF. And this joint distribution C here, you call the copula. So this here you call the copula, but you could just make another f here if you like, maybe f with a subscript c. So here that's also just a cumulative distribution function, but we use now here the values that we have here on. We don't use the original x1, xd. You use now those transformed values which were transformed by the marginal CDFs. So we don't use the x1s and x2, okay, here, or x and y. We use the u's here. So those x's here are transformed by this marginal CDF, and this u here goes into the copula joint distribution. And also here those u's go, so the u2 here, or whatever you call it, goes into the joint distribution. Okay, so that's basically explains it. Maybe if you have problems here, okay, listen to that. So we have here a way of modeling joint distributions. And we can actually model joint distribution in two steps. We look first at the marginal distributions. We get those u's. We call those u's and actually pseudo observations. And then we look for the joint distribution of those marginal u's here. And this joint distribution we call the copula. And the class theorem tells us that this copula is actually unique. That's actually important. Now we derived here equation 21 last time. So take now those u's and put them into the copula. That's what I already have done. So this slide is just repetition. So take those U's and put them into the copulas. So I have here now those U's. So the xi here are realizations of the random vector x1 up to xd. Those are our original variables. And those U's here are those realizations transformed by the marginal distributions, actually to be specific on it, by the marginal CDF. So here I'm just repeating. They are transformed, those x's are transformed by the marginal CDF, and then you have here the U. And you also do it here. So they are transformed, those x's are transformed by the marginal CDF. You see I have here a subscript, so those are marginal CDFs. They give me the U's. You can actually put this in here, okay, for those f x's, and then we get 24. So note that the U's are uniformly distributed, whereas each argument xi can have any distribution. So the original data x, they can be normally distributed, as in my example, but they could also have the gamma distribution and so on. So those marginals here, I have here an example where it's probably a normal distribution when you look at those histograms, but you could also have something with a skew, and then you would have a gamma distribution, or this could be a t distribution, or whatever continuous distribution that has an inverse. Okay, that I think really explains it. Maybe you have to re-listen to this. And why is it important for us? You see, we would like to know joint distributions. In portfolio analysis, if you have maybe those random variables are returns to shares. And then as an investor, you would like to have the distribution of the return of your entire portfolio. Also, we said insurance companies, they invest in a lot of shares. And so here then we have a joint distribution of the returns of those shares. Then we can use it actually, we can actually model this joint distribution. We don't have to model it directly. We can actually model it with a Copula approach. Also in insurance, maybe those random variables are the losses from different types of insurance contracts that the insurance company is selling. And then also the insurance company would like to know what is now the joint distribution of all those losses. And then this will determine what kind of insurance premiums that the insurance company has to charge. Again, they can, this joint loss distribution, they can model using the Copula approach. I was at the World Congress of Mathematics and Insurance and Economics about a few years ago, and I must say about a third of the papers were about Copulas at that Congress. It's a huge Congress, it was Hong Kong, several hundred people took part there. But Copula was an important topic at that Congress, maybe a third of the papers. Now, let's now the inverse function of the marginal CDF. So I have the U, but I have now apply the inverse function. This gives me the X. Let's again look at the graph, what we are doing here. So here I'm giving now the u, and I would like to have the x. So you have to look at the inverse function. That's why it's important that there is an inverse function here. You would have problems if you have flat portions here in the CDF. So the u is given, and we now solve for the x's. So that's the inverse function. It's also called the quantile function. So the inverse function. So that goes here. I'm using now proposition 2. So you can plug this in here with the f. So plug this into equation 24. So instead of the x's, you write now here's the inverse functions for those x's. And you get this expression here for the copula. Now that's actually then this equation is used, okay, to determine the copula. You have the use, okay, those pseudo observations, and you apply the inverse of it, and this gives you the copula function. Now here's that something, okay, just a little bit of explanation, as that's not used in practical work, but it's just showing you that the copula makes sense. So let's now differentiate equation 21 d times. This gives me the joint PDF of x1 up to xd. So I go to equation 21. I differentiate now this d times. So d times, you get this very large cross derivative. And that's actually the PDF. We discussed this before when we did a little bit of repetition of statistics. I did it for a bivariate probability. You see, you have here, if you differentiate, here it's just bivariate, an x1 and an x2 or y. Now, if you differentiate now this twice, okay, if you make the cross derivative, you get here the joint PDF. That's here because of this fundamental theorem of multivariable calculus. You differentiate with regard to x and y up here, and so you get now the f value at the point x and y. Okay, that's the fundamental theorem of multivariate calculus. And that's what I do now here. I have now here d random variables. So you differentiate d times. So it's a cross derivative, okay, d times. And I will get the joint PDF, probability density function. So here, that's differentiated now, d times. Here I have a cumulative distribution function, but differentiation brings me then to the probability density function. I move from the CDF to the PDF. Okay, that's what I have here. So that's now the joint PDF for all those d random variables. And then you also do it on the right side, naturally. So you also have to differentiate here on the right side. You also do it d times. You get here, if you differentiate d times, you get here now the PDF of the copula. So we move here from the CDF of the copula, we move also to the PDF. And then you have to be careful here. You see inside there's also functions here. So you have to apply here the chain rule. So here I also differentiate the C function d times, but then you have to multiply with those variables, with those functions here. That's coming from the chain rule, because you also have to do the differentiation of the functions of the functions inside of the chain. So we see here the joint PDF of the original distribution is actually equal to the joint PDF of the copula. And then, okay, here I have the multiplications of all those PDFs. So that's a multiplication here. That's under independence. So you see, you just simply multiply those frequencies. So that assumes here independence. That holds for independence. Be careful here. You see, here I have commas. Here I have a comma. Here I have a comma. Here I don't have a comma here. I don't have a comma here. So I mean here a product. That's a multiplication here. And it's coming from the chain rule. Naturally here, I also don't have commas. That's just a cross derivative. Okay, d times. Now for this here, we can now just use now a new notation for the copula PDF. Just use a smaller c, a small case c. Remember, for the CDF, cumulative distribution function, we always use capital letter C, capital letters, a big F, and for the PDF, we used small f. So here we also just use the lowercase c for the copula PDF. So you use now here the notation small c for the copula PDF, and then you rearrange. Okay, you're getting this here. So the copula PDF is actually a PDF of the original distribution divided by the product. So here it is a product of all those partial derivatives here. And then you can also use equation 24 instead of the x's right now, again, f to the -1. Apply the quantile functions and you will get this. So this equation is used, okay, when you want to derive the copula density function, okay, the small c. Okay, that's a bit more demanding from a mathematical point of view. In the end, the applications of the copula is actually quite easy. Okay, you will see this in my paper on the quantity theory of money. Okay, so it's that's why it's so popular, because it's very easy to apply. But the mathematics and to understand it for the first time, maybe it's not so easy. So invest a bit of time here. Now we have here an invariance proposition. If your random variables x1 up to xd, if you transform them, and let's say the transformation is a strictly increasing function, then it does not matter for the copula. You have the proof in McNeil. Now it's naturally very important. So let's assume we have an economic problem or a problem in finance, and you express everything in dollars. Now, if you express, and then you get some copula. If you then express everything in cents, you will get the same copula. You see, cents and dollars, that's naturally strictly increasing transformation. That would be silly, okay, if we get as a copulas, if you move from dollars to cents, okay, in an economic or financial problem. You also, what it also allows you to do, you can actually normalize the data. So for example, from your axis, you can subtract the mean, you can divide by the standard deviation, you can normalize those x values. That it does not matter for the copula. So this normalization, this invariance proposition is actually quite important for practical work. Now let's make examples. It's getting a bit easier here now. Let's assume x1 to xd are independent. Independent random variables. Actually, then you could take the so-called convolution Remember, okay, that we discussed in the chapter on insurance supply. So let's assume they are independent. What we get here is so-called independence copula. In equation 21, you just simply multiply those probabilities. So here in 21, you have now the joint probability, but that's now just f times x1, f1, x1, f2, x2, and so on. You just simply multiply the probability of each random variable because they are independent. So here you just can multiply f1, the probability of the first, probability of second, because they're independent. And you this will then actually, if you have that, okay, we can define here the independence copula. So I'm going here to equation 21. Here again, I have the u1 up to the ud. Okay, naturally. So you can plug in now for those f1 up to, so plug in here u1 up to ud. That's coming from equation 20. Remember, those are just the values on the transformed values on the upper axis. Yeah, I'm repeating here a bit. Those are the axis, those are, so you have just the transformed values on the upper axis here, the u1, so that those are the f1, x1, okay, that's coming from this CDF, marginal CDF. So right now the u's here, right, the u's here, and so the independence copula is just a product of the use of the different random variables. That's not so surprising, naturally. And as I say, this amounts to the convolution that we did in the earlier chapter. Now let's look at the Gauss copula. The Gauss copula is based on the normal distribution, naturally. Now, if you use now here equation 26, it seems that I'm using here 26. Okay, that's right. Okay, for the Gauss copula, instead of the f, now I use a phi. Okay, I just use the Greek symbol for the normal distribution. So I mean here again the CDF, and here I mean the CDF, the inverse of the CDF of the marginal distribution. So here you have now the CDF of the normal distribution. It's Gaussian, so it's parameter. It's maybe it's parameterized by the correlation matrix P, and the correlation matrix P has natural dimension D. Okay, here we have D variables. So here I have a D-dimensional normal distribution that is parameterized by the correlation matrix P. So I no longer write here an F, I just use a different letter here, because now here it's a Gaussian distribution. And the notation is here that it's parameterized by the matrix P. The Gaussian distribution is naturally just parameterized by the means and the standard deviations, by the correlation matrix. And here, okay, let's also assume that the marginal distributions are Gaussian. So I use, but those are univariate. Those are the F1 up to FD. But because they are now all Gaussian, I no longer, they're identical distributions, so I no longer have a subscript here. In 26, I used, you see, I used F1 up to FD. We had D marginal distributions. Now they are all the same, they are identical, they are all identical Gaussian distribution. Let's assume they have the same parameters. and so I no longer use actually here the subscript. And we really have to be very careful here about the notation. So those are now identical univariate Gaussian distributions, which we apply to the marginal distributions. So that's what I'm saying here. This V is a standard univariate normal distribution. So actually here I assume that the mean is 0 and the standard deviation is 1. Now let's assume that y is a d-dimensional normal random variable with mean mu and covariance matrix sigma. So y has a normal distribution with a mean mu, okay, and covariance matrix sigma. It's a vector y. Okay, so we have here d random variables. Now, when you normalize, then let's normalize those y's, and then you get the x. So here now the mean of every random variable is 0, and we get okay. Then the matrix becomes the P matrix. Okay, the correlation matrix. So that's this one here. You do this through the normalization. So you subtract the mean, you divide your observations by the standard deviation. Now, the invariance proposition that we discussed before actually means that the copula is the same for the x and the y. So normalization does not matter. That's why this invariance proposition that we just discussed is important. So you can normalize your data. Okay, that's what I have on the Gaussian. Now let's simulate a Gauss copula. Now, for the simulation, you have to do 2 steps. Generate a d-dimensional random vector. So you generate now a random vector, and the random variables have a mean 0, and the correlations between actually follows this P matrix. So we have standardized it. And then return the vector u. You have now those x values here. So you have the x values, and so actually you can now calculate the u vector. Here, that's again, goes through the normal distribution. So you transform now your x values, you transform them into the u values. And the joint distribution of the u's is the Gauss copula. So you do this once, then you do this again and again and again and again, and maybe you do it 1,000 times. So you do here again a simulation. Simulations are very important. You can, if you like, call it again a Monte Carlo simulation. Now here we use it in a completely different context. Okay, so we do the random draws. We generate this random vector. We take the x values. We apply the normal distribution, and then we get the u values. Okay, and the joint CDFs of the u values is the Gauss copula. And don't do it just once. Do it 1,000 times. Now I have you here's a program, and that's what your output will be. So I simulate here a Gauss copula with just for 2 variables, and the rho, okay, is 0.7. So the P matrix is naturally here just 2-dimensional. So I have just a single row here, okay, the correlation between the x1 and the x2. And I've done this 1,000 times. So what I have here on the axis is the u1 and the u2. And this now shows you, okay, the relationship between, the u1 and the u2. So that's a pure relationship between our x1 and x2. which is based here on the copula. We have taken out the marginal distribution. We have used the marginal distributions to calculate the U1s and the U2s, and we show here the distribution that is based on those transformed variables, the U1s and the U2s. That's what the copula gives you. So if you do the program, you don't have to do it for this course, but that would be, you could use this if you do a project. You need the library Copula. So in R, you have to open up, you have to install the library Copula. How to install a library? It's very easy done. Okay, so then I ask here for, I define a normal Copula, normal distribution. Here with two variables, that's the dimension, and the correlation matrix. Yeah, okay, we just have a correlation of 0.7. Okay, between the two variables. And then we do the random vector 1000 times. And this here is just to get a nice graph. Those two commands. And down here, you will actually do, I don't show you the CDF. I just show you the PDF of the copula and I show you the perspective here. So that's a PDF basically, and that's a perspective you have here. So that shows us the relationship between the two variables, x1 and x2, if we have a Gaussian distribution. And the relationship is actually between the transformed U's. So I have here the U1 and the U2. So this figure visualizes the Gauss copula with a correlation of 0.7 between the two variables. Now, what you now maybe would like to have is not just this relation. You would like to have the relationship between the original x's. So you have now to convert those u's into the x's. You do this through the quantile transform. You take the inverse function for the u's and the x's. So you have all those u's here. Now you would like to transform those u's into the x's. You just take the inverse function of the marginal distribution. Take this quantile transform. So the u's go through the inverse, and then you get the x. So proposition 2 is also important. So that's now just the f to the -1 here. I use here the Greek symbol because now here I'm using a Gaussian distribution. But before we called this the f minus, and always I have here the same distribution, so I don't have subscripts here. So you just continue with the computer code. You have it here, and then you plot it. You see, that's what you get now here. You get the bivariate Gaussian distribution with row 0.7 and standard normal margins. So here I have now the x's on the axis, not the u's. And that naturally looks very much like a Gaussian distribution. And also the 0.7 correlation, okay, goes here up. So that's naturally looks, this result looks reasonable. And we did it actually 1000 times. So you can simulate here your distribution. And that's naturally very important for insurance companies. You see, they can simulate the distributions between two types of insurance contracts. And then actually they can figure out, okay, what is the probability of the overall loss and how much premium income do they need. But you can also use it in portfolio management. So in this example, we combine the Gauss copula with a standard normal margin, storm margins to simulate F. But we could actually have used other marginal distributions, the T or gamma or log normal or whatever. So we are not stuck. You don't have to use the normal distribution. Maybe you have a normal Gaussian copula, but you take other marginal distributions. So that's what I mentioned at the beginning. That also looks very Gaussian. And here's so marginal distributions are also Gaussian, but the marginal distribution you could actually take here a skewed distribution like gamma, or a t-distribution which has fat tails. And so you can actually combine a Gaussian copula with non-Gaussian marginals. It's a very flexible approach to model distributions, the copula approach. So for example, marginals may have the t-distribution. They can be used to when assets returns have fat tails. That happens quite often in foreign exchange markets. And the gamma or log normal distributions, those are skewed distributions. You would actually use them in insurance. Okay, so that was quite a lot today. So maybe look at this again, and then we are now almost through the chapter here. We will do a little bit of repetition next time again, and we also introduce another copula. Okay, so maybe I refer again to my paper on the quantity theory. But it will now again become easier. So the main material on copulas we have now discussed. Thank you.